Okay, this BC problem 2007. This is Form A, and this is number 3. This is the graphs of the polar curves r equals 2 and r equals 3. Cosine of theta are shown above. The curves intersect when theta is, well, that's nice. They give you the intersection. 2 pi over 3 and 4 pi over 3. I kind of found it over here because sometimes they don't even give you that, so that's easy to find. Okay, let R be the region inside the graph of r equals 2 and also inside the graph of the cardioid, 3 plus 2 cosine of theta, as shaded. So this was actually the shaded region over here. All this, actually. If you look on your sketch, all this inside this little part over here, this little dimple here is all shaded, not outside the circle there. Okay. Let R be the region inside the graph of the circle and also inside the graph of the cardioid. So inside the circle and inside the cardioid, here's the cardioid. That's what we want. So we don't want this part that's outside the circle. Okay, so find the area of R. So they've got that shaded in. I hope you can see it. But it's this region over here. Well, what I did was I looked at it. I knew they intersected at these points. Well, this is the 2 pi over 3, which is 120 degrees, and this is 4 pi over 3, which is 240 degrees. So in a whole circle, there's 360. This is one third of the circle. So this is 2/3 of the circle, and what I shaded in as red was the part of the circle that I've got here. So again, my lines that go through here, those are the angle measurements. If I without thinking about the angle measurements, if I just think about this circle, because I don't want to have to go from here to here, I just think about the circle, I actually basically just have 2/3 of a circle. So this red part is just 2/3 of the area of a circle, which is of radius 2. All right? So that's the red part. So now how do I find this little pencil part in here? That's the rest, that's also part of the cardioid that's inside the circle, without dealing with this part here. Well, I don't worry about the circle, then just worry about the cardioid, and it's going to be the integral from the cardioid, and this is from 2 pi over 3 to 4 pi over 3. So if I integrate from 2 pi over 3 to 4 pi over 3, the cardioid, I'm just going to get this little penciled section here. Okay? This little section that I put in pencil. Probably could put it in green. That might make it a little bit easier to see. See if that'll help. So here's the cardioid, and it comes around here like this, you see. So that's the part of the cardioid. So if I take that from there, I think that's easier to see now. So a little green section there. Hope you can see that now better. That's part of the cardioid. See, this is the cardioid goes like this. It goes, cardioid goes from here, I'm sorry, right there, all the way around like this, like this, like this, like this, like this, and back over there. So the part of the cardioid from 2 pi over 3 to 4 pi over 3 is just that little green section. So if I take that green section and I add it to the red section, okay, what I end up with is that the region that's inside the circle, that is also inside the cardioid. Okay, so the part that's inside the circle that's also inside the cardioid would be the red and the green. Okay? So I hope that makes sense. So that's kind of tricky, all right? So it has to be inside the circle and the cardioid. This part here is inside the circle but not inside the cardioid. This part here is inside the cardioid but not inside the circle. So that's why we got the red and the green. Okay? So if that makes sense. So in order to find that, we just have to add 2/3 of the circle, 2/3 of the circle, plus the integral of from the cardioid, the area of the cardioid, from 2 pi over 3 to 4 pi over 3. Okay? So I just wrote it over here. 2/3 of a circle is 2/3 pi r squared. The radius was 2, so 2 squared is 4, so it's 2/3. Okay, pi over 2/3 pi times 4, or 8/3 pi. And then this is going to be this integral here. So what I did was I actually put this in y1. I took 1/2, and I did the integral y1 squared. That's going to give me the 3 plus 2 cosine of theta squared, all right? With respect to x, and then from 2 pi over 3 to 4 pi over 3, I multiply that by 1/2, and I got 1.99289. And I added this. I had this all set. I added this to 8 pi over 3, and you end up with 10.370. So you should be able to work that out without me showing you on the calculator, just to save time, okay? So again, this is the integral squared. I put this, like I said, I put this in y1. You could put it right in the Math 9 like that if you wanted. So you could put this in Math 9 if you wanted. X, 2 pi over 3 to 4 pi over 3, multiplied by the 1/2, don't forget that. That's what you get. Add this to 8 pi over 3, and you get 10.370, and that's your area. Okay. Part B. Okay, the particle moving with non-zero velocity along the polar curve is given by that, has position x at t, y of t at time t with theta equals 0 when t equals 0. This particle moves along the curve so that, so it's moving along this cardioid, okay, so that dr dt equals dr d theta. So find the value of dr dt at theta equals pi over 3 and interpret your answer in terms of the motion of the particle. Okay, so dr dt is the same thing as dr d theta. Well, can we find dr d theta? Well, dr theta, r is this 3 plus 2 cosine of theta, so dr d theta is just negative, and the derivative of the cosine is just negative sine, so negative 2 sine of theta. That's dr d theta. And then if we evaluate that at pi over 3, that's going to be negative 2 sine of pi over 3. That's going to be negative 2. And the sine of pi over 3 is just the square root of 3 over 2. That's just going to be negative the square root of 3, which is just negative 1.732. So this is negative. All right, so we want to interpret that. So since the dr d theta is less than 0, okay, dr d theta is less than 0, and r is greater than 0 when theta is equal to r, the actual value of r, this r is greater than 0 when theta equals pi over 3. Okay, so just to find out where the position is, where r actually is, so the position is greater than 0, but it would have to be anyway because r is always greater than 0. The particle is moving closer to the origin. Why is it moving closer to the origin? Because the dr dt, which equals dr d theta, but again, this is dr dt. They tell us that these are the same. The dr dt is negative. So that means as time is increasing, all right, dr dt is decreasing. Okay, and that's my rate of change of my radius, so my radius is getting smaller. So I'm getting closer to the origin. Okay, all right, and then the C part. For the particle described in part B, dy dt equals dy d theta. So dy dt equals dy d theta, and we want to evaluate those at theta equals pi over 3 and interpret your answer. Well, this is a little bit different. So we already had r d theta, so we can figure out what y is. So they want us to find dy dt. So we have to put this in terms, well, actually it's dy d theta, but it's going to be a little hard to do that. So we could do it like this, because we can get dr d theta, but we got dy dt and dy d theta. So we're going to have to work with dy dt. So how can we make this, or dy d theta, so how can we make this into sine of theta without the r, because we've got two variables? Well, what is y equals r sine of theta, because we had this. So in order to get this in terms of y, rather than theta, because we want dy dt, not dy d theta. Okay? Then we just take the derivative of this. Well, first of all, we have to change it so y equals r sine of theta. So this is r, this is sine of theta, so that's my y. So if I want to take dy d theta, which is dy dt, if I want to take dy d theta, I can do it like this. Okay? So that's y. Okay? So here we were finding dr d theta, which equals dr dt. Here we're going to find dy d theta, which equals dy dt. So we take the derivative of this, and we just want to evaluate it pi over 3. So what I did was I didn't want to mess with it using the product rule, so I just put it in Math 8. So Math 8, and I put my 3 plus 2 cosine of theta times the sine of theta, x, and evaluated pi divided by 3. And what I got was 0.5. So that's dy dt, but that is also dy d theta. All right? Okay, for y greater than 0, when theta is greater than pi over 3. So what does that mean? If dy d theta is greater than 0, or dy dt is greater than 0, but actually dy d theta, that's what we're interested in, the particle is moving away from the x-axis because the vertical position is changing. So the particle is moving away from the x-axis because the rate of change of dy d theta or dy dt is positive. So my rate of change is positive, so my y is moving away. All right? So if that makes sense.